Welcome to my tutorial on object detection as a machine learning problem. My name is Girshick. I'm a research scientist at FAIR. Modern object detection systems are complex. They contain many design choices and hyperparameters, and if you're new to the area, it may be particularly confusing to understand why they look the way they do. For example, why is cascaded prediction a recurring design motif? What is non-maximum suppression? And why do detectors need to use it? The goal of this talk is to start from object detection as an abstract mathematical problem statement and then chart the path to present-day detection systems. My hope is that this broader perspective will reveal the principles on which these design decisions are based and expose opportunities for new ideas. So let's start with the abstract problem statement. An object detector aims to answer the question, what objects are in an image and where are they located? To design an object detector, this abstract problem statement needs to be operationalized by making concrete choices. The first choice is to cast the question within the framework of machine learning itself. That is to say, we will develop a model with parameters that will be fit to pairs of input-output data. Note that this is a choice and stands in contrast to using hard-coded rules with no learning. Now the input is simply an image, and the output is any finite subset of the possible boxes in an image. Note that this set of boxes is theoretically infinite in size. Further, for each box in this subset, the detector must output a category label. In machine learning, we only know how to do a few things well, so we will approach the problem using our toolkit, focusing on classification and then later regression. Having settled on using a machine learning approach, our next step is to treat object detection as a classification problem. We will say that object detection is the classification of all boxes in an image. This choice is the classical strategy that has been used for decades in a vast number of papers on object detection. Let's formalize the classification problem. First, we have the label space. It consists of C categorical labels for the objects in the vocabulary, for example, car, person, cat, bus, and so on. And one catch-all background label to indicate that a box does not correspond to any of the foreground categories. These labels will be applied to the boxes denoted script B in an image. We assume that a true classification rule exists that maps the set of all images to the set of all labels. This rule simply applies the correct label to each box. Since we do not have access to this theoretical true mapping, our goal is to specify a model that will learn this mapping. Our decision to pursue this path will lead to a cascading set of technical challenges, which we will now dive into. I'll start by outlining 4 problems before treating each one in depth. The first problem, which you likely anticipated, is that there are simply too many boxes to classify. In response to this problem, the standard solution is to pivot to a proxy problem. We will then show that the true classification problem is not well defined for the output space of the proxy problem. Therefore, we will have to design a new mapping that we want our model to learn. This design necessarily deviates from the original true mapping and involves heuristic decisions. A consequence of these heuristic decisions is that a model will, by design, output redundant detections. Since we do not want these multiple redundant detections for each object in an image, a further step must be taken to remove this redundancy by performing what is essentially a clustering operation. Finally, there is a fourth problem, which is more intrinsic and not a direct consequence of the first 3. This is the challenge of training a classifier on heavily imbalanced data. In the case of object detection, the number of foreground boxes is typically small, while the number of background boxes is very large. This challenge has led to the design of various solutions. Let's dive into problem 1, too many boxes. As we noted, the detection output space is infinite. So rather than working with this infinite space, we will approximate it with a finite set of boxes. You can think of this as a quantization of the original continuous space into a set of representative boxes. The proxy problem will now involve classifying each of the quantized boxes rather than the original boxes. Naturally, most boxes in the original space do not correspond exactly to any quantized box. So even if we can train a model to classify them, thus answering the what part of the detection question, the localization or the where part of detection may be inaccurate. This fact is illustrated in the figure where the gold box denotes the ground truth and the green box denotes the nearest quantized box. The distance between these boxes is the quantization error introduced by the approximation. To address this loss of localization accuracy, we can introduce an additional task. We can add a regressor to the model that will be trained to predict the quantization error. If it can be trained well, the regressor will transform the inaccurately localized quantized box into an accurately localized box. To recap, to address the problem of too many boxes, we have switched to a new proxy problem that now involves both a classification and a regression task. I will now briefly illustrate this proxy problem with 3 examples. In the interest of time, I can only provide a superficial overview of each. I encourage you to read more about each one by following the references in the slides. The first is from before the current era of deep learning. It involves deformable part models, or DPM for short. In DPM, the quantized set of boxes is the set of all sliding window positions in the histogram of oriented gradients feature pyramid. Classification is performed by solving a matching problem between the templates in the model and the Hog features. And finally, a regression is performed to predict the detected object's bounding box. The second example is RetinaNet. RetinaNet uses anchor boxes, which together represent the set of quantized boxes. The network contains a classification subnet that predicts the posterior labeled distribution for each anchor box, given the feature associated with the anchor. In parallel, a regression subnet predicts offset vectors that transform the anchor into the predicted box. More recent detectors, like CenterNet and FCOS, predict boxes from a finite set of points. From the perspective in this talk, we think of these points as infinitesimally small boxes, and we refer to them as point anchors. Each of these point anchors is associated to a feature vector that is used to predict class labels and perform regression in a similar way as RetinaNet. I hope these examples provide context about why so many detection models share the classification and regression design motif. I also want to note that this existed well before the modern deep learning era, because it's a fundamental consequence of adopting the quantize and regress proxy problem. Now, I want to move to the next technical challenge. If you recall, the true mapping that we want our model to learn assumes that the model can exactly output the ground truth boxes. This assumption does not hold, however, in the proxy problem, and therefore the classification rule is not well defined for the proxy problem. To illustrate this point, consider again our example image and the gold ground truth box. Now we overlay the set of quantized boxes in green, and note that the ground truth box is not contained in this set. When introducing the proxy problem, you might recall that I said, the proxy problem will now involve classifying each of the quantized boxes rather than the original boxes. Now, the astute listener will have noticed that this task doesn't actually make sense, because the quantized boxes should all be labeled as background, assuming that none of them correspond exactly to the ground truth objects. And therefore, no objects would ever be detected. Therefore, we need to redefine the classification rule to something that is more sensible. To do this, we will specify a label assignment rule that will assign a foreground label to some of the quantized boxes. The standard approach is to define labeling heuristics based on various criteria, such as intersection over union, or IOU thresholds, or to use measures of centeredness and containment. For example, if the IOU between a quantized and ground truth box surpasses a threshold, as in this example, the quantized box may be labeled with the foreground object, T-Rex in this case. Or, if the IOU is too low, the label will be set to background. There are several important implications of such assignment rules. First, under the original classification problem, each object corresponds to exactly one box. However, now there may be more than one quantized box that is associated with each object. Intuitively, you can think of this as spreading the object's label to multiple nearby quantized boxes. Second, the models like the ones that I described in the examples earlier will make independent predictions conditioned on the features for each of the quantized boxes. The result will be redundant detections, typically many for each object, and therefore a set-level operation is required to resolve this redundancy. Now let's dive into this issue in greater depth with an example. Suppose we have the ground truth box in gold and two quantized boxes that are both assigned the same label as the gold box according to the assignment rule. The prediction from the first box may look something like this. It's a good prediction. The second prediction may look like this. It's also a good prediction. Now note that because both predictions are good, they are also very similar to each other. This is no accident. In fact, this kind of redundant output is exactly what we asked the model to do when we formulated the assignment rule. There is a standard solution to this problem, which is decades old and still used in common practice. So suppose that we have duplicate detections like the ones I just showed. Well, in reality, it will look much more like this picture, or with even more redundant detections. The overlapping boxes are replaced with a single representative by clustering them. There are many possible implementations of this clustering. A common algorithm involves greedily selecting the boxes with highest confidence while suppressing lower confidence detections that have high overlap. Now, let's move to the fourth and last technical challenge. Unlike the others, which were deeply linked to each other, this one is independent. It has to do with the imbalanced nature of the classification task at hand. In the case of the original classification problem, before we did any quantization, the imbalance was infinite. There are finite objects in an image and infinite background boxes. After quantization, the situation is a bit less grim. However, the foreground labels may still only account for 0.01 to 0.1% of the total labels. We know that from beyond the context of object detection, training classifiers on imbalanced data can be difficult. If nothing is done, then classifiers may simply ignore the minority class, which can still lead to near 100% classification accuracy while producing a no-good terrible object detector. The second entangled issue is that of processing speed. A system that spends a lot of computation classifying background boxes may be needlessly inefficient. There are several classical solutions. The first addresses imbalance via the loss function used to train the classifier. Consider a linear classifier parameterized by a weight vector W and bias B, as illustrated on the left. The margin is the sign distance of a data point to the decision boundary, and we can look at various loss functions as a function of the margin on the right. Informally, we will divide the data points into 4 groups. The first are easy foreground examples. These are foreground examples that have a large margin. Next are hard foreground, which are foreground examples that are near the decision boundary or on the wrong side of it. Likewise, we'll have hard background examples and easy background examples. Note that there are typically a very large number of easy background. Intuitively, these correspond to boring background patches found all over images that clearly do not belong to any of the foreground categories. These are typically easy for classifiers to reject, and there are a lot of them. Commonly used loss functions, like cross-entropy, are sensitive to this large cloud of easy background. This is because the loss associated with these large margin points does not approach 0 fast enough relative to the number of such data points. The result is that they can have an undesired influence on the learned classifier, leading to poor detection performance. A better loss function for detection will not be influenced by this cloud of easy examples, and instead will be influenced primarily by the hard examples. In general, this property is referred to as hard example mining. One such example of a loss function that has been recently used with good empirical results is focal loss. The second solution is to use a cascade of classifiers. Each stage in this cascade is usually designed to be relatively fast, but may also be relatively inaccurate. Early stages are tuned for high recall, so that true positives are not lost, but while also removing a large portion of false positives. Gradually, this alleviates the imbalance, and the later stages see more balanced data. We can view this process from the perspective of our linear classifier shown earlier. In stage 1 of the cascade, it rejects a large number of easy background examples while retaining all of the foreground, i.e. the green points. The second stage now gets a more balanced problem. Likewise, it rejects many of the background points while retaining the foreground ones. And this is repeated so on until the final classifier operates on a reasonably balanced data regime. This classic solution was made famous in the pre-modern deep learning era by the 2001 paper from Viola and Jones. Now, in the modern deep learning era, it continues to see extensive use. Examples include the RCNN family of models. A third approach to imbalance is also worth mentioning. In this approach, the quantization is extremely aggressive, so that by design, there are not many output boxes. With few output boxes, the degree of imbalance is bounded by construction. This is the approach that was used in the original YOLO paper. And with that, I would now like to briefly summarize the classic approach to object detection. In this approach, object detection is treated as a machine learning problem. The machine learning toolkit has highly developed techniques for classification. And therefore, unsurprisingly, detection is cast as a classification problem. In particular, the task of classifying every box in an image. This hits an immediate obstacle. There are simply too many boxes to classify. A natural solution is to consider a finite subset of boxes by defining a proxy problem. The most common choice is what I refer to as the quantize and regress approach, where the space of all boxes is quantized and the model attempts to predict the quantization error. With this proxy problem, there are a large number of degrees of freedom. Over the years of research on object detection, researchers have largely relied on their geometric intuition, or what one might call a domain-specific prior, to explore these degrees of freedom. This intuition has guided the design of quantization, labeling heuristics, how the regression task is parameterized, algorithms for performing non-maximum suppression, cascades, region of interest operations, and so on. What I want to highlight here is the use of geometric entities, such as boxes and now commonly points. I refer to these as the fundamental substrate because it is the underlying layer upon which everything else is built. The detector makes predictions for each quantized box, and during training, each quantized box is compared to the ground truth in order to derive its labels. A second commonality of the methods following this classical approach is that the learned part of the model makes independent predictions for each geometric entity, conditioned on the features computed for each entity. Non-maximum suppression is the only set-level operation that resolves conflicts between these independent predictions, such as redundant detections. For the most part, the non-maximum suppression is not learned. There are a few exceptions to this, for example, the work of Hu et al. On relation networks for object detection. Now I want to offer a higher-level perspective beyond the scope of the classic method. The perspective starts from the view that object detection is a very challenging input-to-output mapping problem. This abstract mathematical problem is modeled as a machine learning problem. The machine learning problem is itself a proxy, and the specification of it involves introducing new assumptions and approximations. The choices that are made may introduce new subproblems that require solving. Most of the research on object detection focuses on solving these new subproblems, so it effectively operates one level below the original object detection problem. However, larger changes are possible that involve rethinking how the machine learning problem is thought of in the first place. And by doing this, we may arrive at different and hopefully more tractable problems to solve. And now I think that we are starting to see some exciting new research that pushes exactly in this direction. In particular, I would like to highlight the work of DETR, or Detection Transformer, from my colleagues at FAIR. In brief, DETR uses a transformer on top of a standard convnet in order to predict object classes and locations. The model is simple and elegant, and I refer you to their archive paper for the full details. What I would like to focus on here is that DETR uses a different kind of fundamental substrate. It uses a set of object queries, which are simply learned vectors. They interact with each other and with the image features inside the transformer decoder. What differentiates these queries from the classical approach is that they do not have a prior geometric meaning. A category and box is predicted for each query. These predictions directly form this output set predicted by DETR. It is taken directly from the model without applying a classical non-maximum suppression algorithm. Because the model produces the output set directly, rather than relying on defining a classification and regression problem on quantized boxes, it avoids the label assignment heuristics that we discussed earlier. Different from the classical approach, DETR does not follow the quantize and regress paradigm. Instead, it operates directly on a set of entities that do not have prior geometric meaning, though through the process of learning, they may develop a learned geometric meaning. DETR, like classical approaches, does make independent predictions for each object query. However, the transformer is a permutation invariant set-level operator that enriches the object query features with enough information such that non-maximum suppression can be learned. I think DETR represents an exciting example of how rethinking the fundamentals of object detection as a machine learning problem can fundamentally change the models and challenges that we face in research. And with that, I would like to conclude and thank you for your time.